Loop quantum gravity. Loop quantum gravity is another theory attempting to merge quantum mechanics and general relativity, focusing on the quantum properties of the gravitational field. It suggests that space itself is granular and made up of tiny loops of quantum threads, offering a different perspective on the fabric of the cosmos. Welcome to Top Thangs. Step into the quantum realm where space and gravity weave the fabric of the cosmos in ways you've never imagined. Today we're exploring loop quantum gravity, a revolutionary theory that challenges our understanding of the universe. Join us as we unravel the quantum threads that could tie together the biggest mysteries of physics. Exploring loop quantum gravity, a theory of quantum space and gravity. Unifying quantum physics with gravity remains the holy grail of theoretical physics. Loop quantum gravity offers a unique approach focused on the quantum properties of space-time itself. Today we will dive deep into this fascinating speculative theory proposing that space consists of quantized loops and gravity arises from interactions between them. We will unpack the conceptual foundations of loop quantum gravity, how it mathematically models the fabric of the cosmos, and its major insights. Key evidence and open questions will also be evaluated. If validated, loop quantum gravity could provide the elusive quantum theory of gravity. This tour through the loop approach to quantum space and gravity illuminates an intriguing direction for comprehending physical reality's deepest workings. Background on quantum gravity theories. Reconciling quantum mechanics with general relativity ranks among the most profound challenges in physics. At cosmic scales, gravity rules through space-time warping. But zooming to quantum realms, matter behaves probabilistically as particles and waves. No overarching theory yet accounts for this conflict. String theory posits gravity originates from the quantum vibrations of one-dimensional strings. It elegantly unites fundamental forces by modeling particles as higher-dimensional strings. Loop quantum gravity provides an alternative perspective by building quantum properties directly into space-time geometry itself, through discrete loops. Developing successful quantum gravity theory promises to revolutionize understanding of the cosmos. Framework of loop quantum gravity. Loop quantum gravity reconceptualizes space-time as a mesh of discrete quantized loops rather than a continuous geometrical fabric. These fundamental loops constitute the building blocks of quantum space down to the Planck scale, much like atoms in matter. Their woven interactions give rise to the macroscopic effects of gravity and bent space-time. This approach applies quantum field theory adapted to Riemannian manifolds of general relativity, describing curved space-time. Specific quantum variables represent geometric measurements like surface area and volumes of spatial regions. Quantizing these geometric variables casts the gravitational field into tiny, Planck-scale quanta of discrete loops. Quantum loop dynamics account for microscopic properties while averaging outward into the smooth space-time curvature of general relativity. Modeling the gravitational field through quantum loops in this manner allows deriving macrogravity from an underlying quantum substrate. Major insights and predictions. Several key insights emerge from loop quantum gravity's loop-based space-time. Space consists of a quantum superposition of plaquettes woven from discrete loops rather than continuous geometric points. This granularity provides a minimum length scale. Spin networks underlie the quantum geometry, dynamically evolving by interactions between nodes and edges representing interlinked loop states. Black holes likely resolve into elementary loops rather than singularities under this theory. The event horizon may quantize into discrete punctures stemming from loop behavior. Time also exhibits quantum discreteness since loops provide the fundamental architecture of space-time itself. Loop evolution generates a quantum passage of time. Gravitational waves may manifest quantized properties reflecting their origins from quantized loop oscillations. Observing this could test the theory. Overall, loop quantum gravity paints a radically different ontological picture of space itself as a quantum nanoscale network of discrete interlocked loops constituting the cosmic fabric. Gravity emerges macroscopically from the collective behavior of these loop components. Key evidence and open questions. As primarily a mathematical construct to date, loop quantum gravity lacks decisive experimental tests. But several promising directions could provide empirical validation. Precision measurements of gravitational wave propagation may reveal subtle quantum effects implied by underlying loop discreteness. This could verify or constrain the theory. Cosmological predictions about inflation and the early universe offer another avenue to confirm loop-derived models empirically. The cosmic microwave background radiation provides a means for testing. Probing the quantum structure of black holes through their emissions or mergers may uncover signatures of the hypothesized loop transition at the horizon scale, replacing the singularity. Unifying loop quantum gravity with matter interactions has posed challenges requiring extensions to the standard model of particle physics. Developing consistent matter models and unique testable predictions remains an ongoing research frontier. While very speculative, loop quantum gravity shows promise as a foundational ontological description of the quantum essence of space and gravity. Further mathematical consolidation and empirical testing will determine if spacetime actually exhibits an underlying loop weave, as this theory proposes. Philosophical implications. Conceptualizing the universe's fabric as compiled from countless quantum loops leads to striking philosophical reflections. Discrete loops imply a fundamentally granular cosmos down to the very structure of space, overturning the classical geometric view of smooth, continuous spacetime. The classically empty vacuum seethes instead with dynamic quantum fluctuations as loops pop in and out of existence at the Planck scale. Emptiness is revealed as a teeming foam of nanoloops. If time also proves discrete, temporal experience itself fragments into quantum clock ticks, pacing the dance of loops. Duration becomes digital rather than linearly flowing. By extending quantization to the canvas of space itself, loop quantum gravity subsumes even spacetime geometry into quantum probabilities and uncertainties. This radical paradigm shift empowers a view of reality's elemental quantum texture that is discretely woven rather than an amorphous analog continuum at the deepest levels. Navigating the frontier of loop quantum gravity. In the ongoing quest to unravel the mysteries of the universe, loop quantum gravity, LQG, remains a beacon of hope for those seeking a theory that merges quantum mechanics with general relativity. This chapter delves into the latest research and developments within LQG, shining a light on experimental simulations, entanglement in spin networks, and the potential empirical evidence that could validate or challenge this groundbreaking theory. Experimental simulations, bridging theory and reality. One of the most compelling advancements in LQG research involves the experimental simulation of loop quantum gravity using a photonic chip. This novel approach attempts to replicate the quantum geometry of space by simulating specific boundary states, thereby offering a tangible connection between LQG's abstract theoretical predictions and experimental validation. The fidelity between the experimentally measured matrices and theoretical expectations provides a quantitative measure of the simulation's accuracy, revealing both the promise and the challenges inherent in modeling the quantum fabric of the universe. Entanglement, the fabric of quantum space. At the heart of LQG lies the concept of spin networks, a quantum web that underpins the structure of space-time. Recent studies have focused on understanding the various types of entanglement within these networks, including link, intertwiner, and boundary spin entanglement. This research elucidates how quantum states are intertwined within the fabric of space-time, offering insights into the quantum mechanical properties that govern the universe's very architecture. Astrophysical insights, the cosmos as a laboratory. The quest for empirical evidence supporting LQG has led researchers to the cosmos, where phenomena such as black hole shadows and gravitational waves serve as natural laboratories. Observations from the Ice Cube and Fermi observatories have provided data that could be pivotal for quantum gravity research. Meanwhile, theoretical models based on LQG predictions are being tested against the shadows of black holes observed by the Event Horizon Telescope, potentially offering a new avenue to probe the quantum aspects of gravitational fields. Quantum gravity experiments, a leap into the unknown. A groundbreaking experimental project aims to test the quantum nature of gravity by placing microdiamonds in a state of quantum superposition. This experiment, if successful, could demonstrate gravity's ability to entangle macroscopic objects, thereby providing direct evidence of gravity's operation at the quantum level. Such an experiment challenges our fundamental understanding of reality and could herald a new era in quantum gravity research. Global collaborations towards a unified understanding. The Quantum Gravity 2023 Inches Conference in Nijmegen, Netherlands, exemplifies the collaborative spirit driving the field forward. This event brought together experts from diverse quantum gravity approaches, fostering a dialogue aimed at bridging theoretical gaps and pushing the boundaries of our understanding. Such collaborative efforts are vital for the advancement of LQG and related theories as they encourage the exchange of ideas and the integration of complementary perspectives. As we stand on the brink of potentially groundbreaking discoveries, the journey through the loop quantum gravity landscape continues to inspire and challenge researchers worldwide. The synergy between theoretical predictions, experimental simulations, and astrophysical observations is narrowing the gap between quantum mechanics and general relativity, inching us closer to a unified theory of the cosmos. As this chapter closes, we look forward to the new horizons that future research in LQG will unveil. In summary, loop quantum gravity's unique proposition of discrete loops underlying spacetime shows immense promise for uniting quantum mechanics with gravitational reality. Mathematical progress and physical predictions have brought this once obscure theory into the mainstream search for quantum gravity. While open challenges remain, its conceptual insights resonate. Empirical testing offers hope of validating whether we indeed inhabit a universe fundamentally woven from quantum threads of loop geometry. Understanding gravity's quantum essence through the loom of space-time would profoundly complete our comprehension of physical law. Loop quantum gravity invites us to contemplate a universe fundamentally different from our classical understanding. It proposes a space-time fabric woven from quantized loops, where gravity is not just a force but an emergent phenomenon of these quantum strands. How does the concept of quantized loops of spacetime alter our traditional understanding of the universe? What implications does loop quantum gravity have for the future of physics and our quest for a theory of everything? As we journey back from the depths of quantum space, we're left with more questions than answers. Is our universe truly stitched together by quantized loops of gravity? The quest for a unified theory continues, and loop quantum gravity offers a compelling path forward. Share your thoughts and questions below, and let's keep the conversation going. If you're fascinated by the mysteries of the cosmos, don't forget to like, share, and subscribe for more deep dives into the fabric of reality. Thank you for watching Top Thangs. References, sources, and additional info: Rovelli, Carlo, and Francesca Vidotto. Covariant loop quantum gravity, an elementary introduction to quantum gravity and spin foam theory. Cambridge University Press, 2014, Ashtekar, Abhay, and Jorge Pulin, eds. Loop quantum gravity, the first 30 years. World Scientific, 2017, Bojavold Martin, Loop quantum cosmology, Living Reviews in Relativity 11.1, 2008. 104, Agolo Ivan and Parampreet Singh. Loop quantum cosmology, Arxiv preprint Arxiv. 1612.01236, 2016. Smolin Lee. An Invitation to Loop Quantum Gravity, Arxiv preprint HEP-THAT 0408048, 2004. Rovelli Carlo, Loop Quantum Gravity, Living Reviews in Relativity 1.1, 1998. 175, Thiemann, Thomas. Modern Canonical Quantum General Relativity, Cambridge University Press, 2008. Ashtekar, Abhay. New Variables for Classical and Quantum Gravity. Physical Review Letters 57.18, 1986, 2244. Loop Quantum Gravity and Quantum Information, r5iv.org. Unveiling Quantum Gravity. New results from IceCube and Fermi data, phys.org. Tests of loop quantum gravity from the EHT results of SGRA circumflex asterisk, r5iv.org. Quantum Gravity 2023, Nijmegen, Netherlands. Hyperspace at GU, hyperspace.uni-frankfurt.de.